All right, hey folks, I'm back for another flipped video here. Try to make it entertaining for you. I guess I'll start out with a first fascinating fact I was reading last night. I can pull this up here so I can actually read it to you. I was reading about ocean water and how like crazy it is. Ocean water has up to 100 billion viruses in it per quart of water. So like 1/4 of a gallon, 100 billion viruses. If you added up, according to the virologist Dorothy H. Crawford, if you added up all the ocean viruses and stacked them like end to end, they're super small, obviously, but if you stacked them end to end, the distance that they would stretch out would be 10 million light years, which is like an unbelievable distance. It's crazy. So, ocean water, very full of viruses. Uh, I think in this 100 billion viruses that we've tried to identify, we've only found 27 of them that actually can do any harm to any humans at any point in time. And that harm is just basically like a runny nose. So, kind of a crazy place. Anyway, marine bio. I am going to be working on this first part of tide notes today and trying to get you that information. Now, news alert, tides and physical properties of the ocean is really a boring subject. It's not really like a fascinating, really cool thing, but it's amazing how many people in the world live near coasts and have no idea how the tides actually work. And so my job is to try to get you to a point where you actually understand how tides work. Because if you're going to go into marine biology, this is like the first thing that they start with. It's plate tectonics, it's tides, it's like geological features of the ocean. So that's why I'm starting with this. I personally don't find like a huge amount of interest in it, but I think it's really important if I'm going to give you a curriculum that's going to set you up for success as a marine biologist down the road. So here we go. Part one. You can find these notes in Schoology. Underneath here's week one distance learning. And again, it's going to look different for you guys once we get our classes here, but this is just my resource folder. So these are going to be the notes that I'm going to take. They're underneath the notes thing here. I'll say tide notes. That's what's going to open up right here. And then I also created a worksheet here that you can find underneath assignments, and it's worksheet for tides. And make your own copy of that, and then you'll go ahead and you'll answer these questions as you go along. So if you need to pause the video to get to those things, go right ahead. I'm going to go through those notes here in about 5 seconds. So ultimately, what we're going to be talking about here today is the movement of water on Earth. So tides, you can read the definition there, rise and fall of water on the Earth. Any large body of water will experience this. So oceans are usually thought of as tides, but Lake Superior has tides. Lake Superior has a tide of about 1 to 2 inches every day. You really can't measure it though because there's always waves going, and you can't ever measure like the distance of water traveling in waves very well. Tides happen in little tiny bodies of water. Tides would happen in a glass of water. Tides would happen anywhere. Water is fluid because it's liquid, obviously. It's an answer to one of my questions later on. But because it's fluid, it can move, and it moves with forces of gravity and other things pulling on it. So, largest tidal changes in the world, found out this Bay of Fundy in eastern Canada. On a daily basis, the tides are typically 12 to 15 feet. So quite a bit of water moving in and out. You can see like in the background here, like an entire bay has emptied out into the ocean for miles. And this happens every about 6 hours. It goes from looking like this to looking like this. So 6 in the morning, noon, or whatever. So ultimately, there can be a lot of movement of water. And when you're talking about marine biology, that watery environment where all those things live, that's really the important thing to keep focused on. So ultimately, that's what we're going to do. I wanted to make a quick mention of this thing called a tidal bore. It's really not a testable question, but it's really kind of interesting. And I'll let you click on those links yourself if you want to take a look at the videos of them. But tides can move so quickly. And again, it's not something that we're really familiar with here in Minnesota, but they can move so quickly that they actually create like rivers of movement of water coming back and forth. And even outgoing rivers that have current that goes maybe this way, the incoming tide may come over the top of it and actually change the direction of the river during the daytime a couple of times. So really kind of an interesting concept. So again, click on those links if you want to. We're going to focus on the tides as they are. So keys to understanding, a couple of things here. And again, following along with the worksheet as best as I can. The Earth rotates around its own axis every 24 hours. I think most people are pretty comfortable with that concept. You spin around, every 24 hours. That'd be 1 day, right? The moon orbits the Earth every 27 days. This one is an important one for later on, but the moon will orbit around the Earth. So as we take a look at this, here's our moon. If we start out at a full moon, the reason that the moon is full in this diagram is because the sun is over here and the moon is over here. Now, the moon is not really on a flat surface with the Earth. The moon is kind of lifted off of that surface. So it's actually like above the Earth. So the sun might be over here and the Earth might be here. I'm trying to do this in the little screen down there in the bottom, but the moon is kind of like lifted up above that. So the sunlight can shine on the moon and you can get the face of the moon then over here being full. In other words, it's all lit up. So at midnight, when you're in the darkness on this side of the planet, you face the full moon and you see the whole moon lit up. That'd be a full moon. Now, when the moon travels around, realize it's traveling in a counterclockwise pattern here. To get from full moon back to full moon, that's going to take 27 days for that moon to move through that orbit. So like after 1 day, it might be here. After 2 days, it might be here. After 3 days, it might be here. 27 days split into fourths. It doesn't split very evenly or nicely, but let's take it's 28. Let's just say 28 days split into fourths. That's 7 days. It takes a week to go from a full moon to a third quarter, another week to go to a new moon, another week to go to a first quarter, and then about another week to go back to a full moon. So hopefully that makes sense a little bit there. Again, the sun is over on this side. If the sun was on this side, we'd have a different diagram. The full moon would be over here. So keep that in mind. Try to think about that one. And then the Earth is rotating. And notice that our diagram of the Earth here, there's an N right in the dead center of it. That's the North Pole. We're actually looking down on the Earth from the top. So it's not a usual diagram. And what we're doing is we're rotating this way. So the Earth is spinning around this way. How long does it take to spin around one rotation? That's 24 hours. So if you're here at noon on one day, the Earth is spinning, and noon the next day is 24 hours later. In that 24 hours, in that 1 day, how far has the moon moved? Well, 1/27th of the circle. Think about that one. 27 days to go around a full circle. So 1/27th would be about here. And then another day, and then another day, and another day, and another day. And you get the idea, I hope. Okay, so keep those things in mind. Everything rotates counterclockwise here. The sun is over here in this diagram. If it was on the other side, it'd be a little bit different idea. You can take a look at an animation from NASA if it really helps you. It might be a better way to click on that and take a look. Okay, next concept here is that gravity exerts a pull. The amount of pull, the magnitude of pull, is dependent on the distance between the two objects and the size of the two objects. So if you've got a short distance between two objects, there's more gravitational pull. If they're really far apart, there's not as much gravitational pull. And then it's also related to the size of the objects, like really the mass of the objects, how heavy and how dense they are. So the water on our planet is influenced by the moon, not so much the sun. Why? The sun is way far away, and the moon is really dense. It's actually kind of heavy compared to the sun for the distance that it is. So gravity on our planet pulls and pushes a lot more actually from the moon than the sun. And so you have the moon pulling and pulling and pushing and doing all these things. That gravity is impacting us as solid objects, not too much. But if you were a liquid object like water, then that gravity would be impacting you quite a bit. So let's take a look at this figure here. And I say figure weirdly. I know kids make fun of me all the time. You can feel free to laugh at me if you want to. Figure, I guess. Figure 2. So gravity's pulling Earth. The important thing to understand here is that, one, there's also Earth is pulling on the moon too. So there'd be arrows going the other way, but we don't care about that because there's no liquid on the moon being influenced. It's one of the questions on the worksheet, I know. The gravity's pull on Earth from the moon, realize that all of the force is going towards the center of mass of the moon. So that's the way that gravity pulls. Notice that it's going to pull in a straight line at the equator, but it's going to pull in a downward line towards the moon's center from the poles of the Earth. And the same thing is going to go on all around the Earth. Now, if the Earth is kind of rotated this way, or it's, snapshot right here, This place on the Earth, if you're facing the moon, if you're closest to the moon, has more gravitational pull because you're closer to the moon. And if you're further away from the moon, I gotta plug my laptop in. Hang on. There we go. So the gravitational pull on the far side of the moon is actually pretty weak because you're further away. All right. Next concept, figure 3, centripetal forces. Two objects spinning around each other. If you took something and you spun around with it on a string, that thing would want to fly off, but there's got to be a force that pulls it towards the center. That's centripetal force. That's what that word means. So it pulls it towards the center to keep it in an arc instead of letting it go fly off. So anytime that something's in orbit, and this orbit is backwards because everything moves in counterclockwise force here, there's always a centripetal force that's going to pull things towards the center of each other. On Earth, our centripetal force towards the moon, because we're spinning around the moon just like the moon is spinning around us, the centripetal force is equal. Notice how all of these vectors, they're called, all of these are the same size. The force is the same towards the center, and it's all in a parallel motion, okay? So we have two different forces here. We've got gravitational force, which goes towards the center of the moon, and we've got this force that goes towards the moon in a constant force no matter where you're at. Okay, so that's going to be your centripetal force there. Figure 4. Okay, the net resulting forces on the Earth is the direction or magnitude difference from centripetal to gravitational. So what I'm going to do here is I'm going to try to blow this thing up here a little bit and try to zoom in quite a bit here. So here we have, like on this location, we'll take a look right here, this location on the Earth. There's a gravitational force towards the moon. There's also a centripetal force towards the moon. Remember, our difference here are differences from centripetal forces to gravitational forces. So from centripetal to gravitational, if you drew a line between those two, that arrow would be going to the right here, and it would be a short line to the right. That's going to be the overall net force. That's called the net force. That's that blue line. Notice that that net force here on the planet is this way. If we go to this side of the planet, you have centripetal force is still the same. Notice they're all the same size. Centripetals are all the same size. And gravitational force, though, is really weak. And remember that our overall net force is going to be from centripetal to gravitational. So we're going to go an arrow this way to get from the tip of this arrow to the tip of that arrow. We're going to end up with net forces being here. So actually, there's a force pulling that way to the left. That's kind of different. So I hope you saw my daughter walking by in the background there. We have net forces going this way. We have net forces going this way. Well, those are opposite poles. And notice that if we're at the pole, let's look down here, centripetal is here, gravitational is here, the net force is just straight up or straight towards the center of Earth. So what's going on? Well, we have a net force on this side of the planet pulling this way. We have a net force on this side of the planet pulling this way. Net force pulling this way, net force pulling this way, net force, and check these, look at them, think about this, net force pulling this way. All of this is going to be influencing the flow of water. So water is going to move in those directions. So let's go back to our full screen here. Oops. There we go. So figure 5, the overall effect is called the tidal bulge. You're going to have water being pulled this way and water actually being pulled away from the moon. And you're going to have water almost like pushed. It's actually being pulled towards the center and pulled towards the center here. So that's ultimately what's going to end up happening to our diagram, and you're going to end up with a bulge. The bulge is not very big. This is really exaggerated. You wouldn't be able to see it from space. It's only about a foot or two at the equator, but there is a tidal bulge. Okay, so that's the end of part 1 of the notes. Hopefully I've answered all the questions for you. If you have any, email me, get a hold of me. I'll be available for live meetings too. And hopefully that made sense up to this point.